before starting, just to let me introduce you two new visitors. Hélène Olivier and Kevin Berlemont. They come from the Coleman Cachans, close to Paris. They are master students there, and they will be with us working with Claudio and also with Christophe and myself until the end of July. Welcome.
Okay, so shall we start? We have here Ulrich Krause. He comes from the University of Bremen, where he's professor of mathematics. He obtained a PhD in economics from Hannover. You know what Hannover is? You know what Hannover is?
I guess.
He's a mathematician by training. He's been visiting professor of several universities. Has published many books and articles in mathematics. Here in the latest book he wrote on positive dynamical systems in discrete time, which is somewhat related to the topic of the talk. His main interest is in algebra, number theory, difference equations, positive discrete dynamical systems, social, economic, and dynamic modeling, theory of production, decision theory, social choice. Most of us know him for his model with Hesselman about opinion information. Some of us in England, I don't want to wait at here. He's on vacation, yeah, but he could not avoid thrilling of giving a seminar to IFISC.
Thank you very much for your kind introduction, and good evening, everybody. Actually, this to give a talk is a kind of vacation I like very much. And I'm very happy to be here at one of the nicest islands of the world and one of the most beautiful campuses I've ever seen. So you must be very lucky to be there. That's great. And if you think of swarms in the air, then one perplexing thing is, how do they manage to stay together to form a swarm? I mean, there are various formations. You know this G formation or V formation. I mean, this way, horizontal. And also some other thing called echelon, studied by biologists, which is something like this. There is some in the front, one or more birds, and there are others here, distributed here, or from here, or from there, so like a tree. But they are coordinating, but there is still some movement in this frame. And I will talk about this frame, but it's not an exact mathematical frame. And 2 points will be important within the talk and studying a model. That is concerning the interaction of the birds. What is the structure of interaction? And what is the strength of interaction? And actually, I will make some assumptions on this. I will make some little assumptions in addition, but the assumptions on the structure of interaction and the assumption on the strength of interaction. This will be the important ones. Now first, let me show you a famous model of swarm formations. This is Cucker-Smale flocking. This is Stephen Smale, the famous topologist.
Like presentation mode, maybe with control.
Sorry?
Just go on presentation mode. Full screen.
Oh yes. That's very helpful. And I will not go into details. I just want to show it to you. There is in the model, there are n birds in R3, and time is discrete. Discrete period, 0, 1, 2, etc. And xit is the position of bird I at time t in 3 dimensions. And vit is the velocity of bird E at time t. And this, of course, is just a definition of velocity. And this is now the rule how they are interacting. Right? So the change in velocity of a bird at a certain point of time is some way of the difference in velocity to the others here, of this bird. And the important thing is, of course, what do you think about the interaction coefficients here? And this is what Smale and Zucker propose. And the theorem they have is they study the model in continuous time as well as in discrete time. I'm talking about the discrete side of it. And two things are important here. This is symmetric in the birds. You can interchange I and J here. So the interaction is symmetric. This is not very natural, because if you think of formations, this is not symmetric. Birds are seeing birds in front, but not in behind. And the second thing is this coefficient beta here. And also you observe there's always zwischen birds, there is an interaction, because this expression is always positive due to the one here. And the theorem then is they approach a joint velocity. So this is the important thing in swarm formation, after a while having the same velocity. And if one of the following conditions holds, beta, first case, is strictly less than 1/2, or two other cases, if it's 1/2 here, this, then you need an additional condition on the initial velocities of the birds. And in this case, you need even some more on the initial positions of the birds. So as I said, this requirement, symmetry, which is very important if you want to, and there is a paper by Ha and Liu who simplify the model and find symmetry gives them a quadratic Lyapunov function. But this is not the case if there is no symmetry. You have to do other things. And the other point is strong connectivity. Each bird interacts with each other. This is not natural. And actually, there is a nice paper by Bertrand Chazelle. It's a preprint, it's about 100 pages long. And he shows, among others, you don't have in the general case a Lyapunov function, and also convergence is very slow in general. So this is just a look at this. I will come back to this model later on, making some refinements and generalizations. Now, I will use, on my way, opinion dynamics, and more general, the embedding of all the questions of swarms into the area of positive dynamical systems. And there is this model under opinion dynamics under bounded confidence, joint work with Rainer Hexemann and myself. And today I will take something on general interaction of birds, which I took from a book already mentioned before by Raoul. Okay, so look at this. N agents, I talk about agents, could be birds or some other things being able of interaction. And they might be in RD. They might be 3 or something else. The interaction is non-negative and sums up to 1. And the opinion or the state of the system of member I in the next period is given as some average of the opinions that appeared before. But of course, this interaction depends on time. So that makes things difficult. Equivalently, you might say the opinion in the next period lies in the convex hull of all opinions in the period before. That's the same thing. Now this then is what is called all the interaction coefficients form a matrix, which is a stochastic matrix, meaning all entries are non-negative, and in each, the sum of each row equals 1. And those matrices will play a role, and so these are one of positive dynamic assistance. The positivity comes from the positivity or non-negativity of the matrix. Okay, now there are some assumptions. The first one is the interaction is bounded from below by a fixed structure, a fixed matrix, and some intensity. This f is a reevaluated function, assumed to be decreasing, which is not a strong assumption, and A is in a negative matrix. So this fixes a certain structure, and this is a certain intensity. And then comes two assumptions. One on the intensity of interaction, which should not decay too fast. I mean, if interaction becomes too fast, meaning no interaction at all, you will not observe a swarm. Right? And the structure of interaction becomes not too loose, which means, I mean, if there is no structure, the structure is arbitrary, no fixed structure, then you cannot expect the swarm to see. And so this means the intensity, f is the intensity, the integral over the intensity is infinite, which means taken over time, the intensity can decay to 0, but this integral should be infinite. And for some p. And the structure of interaction because means to any agents I and j exists a third one such that those quantities are positive. Those are the entries of the p power of the matrix A. For example, if p is equals 1, this makes sense, and then this means the entries I, aik, ajk are strictly positive. This is called principle of the third agent, or in mathematics, this property of a matrix. You have a matrix, and you have two rows, I and j. And the assumption means there should be one column where the two rows have a strictly positive entry. Right? For two rows exists a k, a column, such that, think of p equals 1, those quantities are strictly positive. And this is called the Kremlin matrix. And there is a lot of mathematics around this kind of matrices. Okay, these assumptions then there's a theorem. Under these assumptions, the opinion dynamics described by this model converges to consensus. That is, the opinions of all agents approach the same value for t going to infinity. And the connection to swarms is that I think of swarms as finding finally a consensus on their velocity. Right? I mean, this is not the same kind as when people are talking to find a consensus. But in principle, it's the same thing. And the convergence is exponential fast, and then you have some sensitivity property here, which is not so important in following. Now I apply this, which is opinion dynamics, to the question, to the model of Cucker-Smale. And then you have this. This is a model, the change in velocities. Here we have this gravitation-like expression of Cucker-Smale. But the difference here is you only sum up over certain birds in a certain set S of I, depending on this bird analysis. And where S of I is a set of birds seen by bird I. I not in the set. The set is so I look at this as follows. If there is a swarm, some birds, and if I look at a certain bird, then the interaction with the others is only with birds he can see. Right? So some cone-like view. It must be not the cone here, I just assume it's a set. So this is unsymmetric. Right? So I consider this asymmetric interaction among birds. And the result then is you get flocking, that is the velocities approach finally all the same value. If this gamma here, this additional assumption, is less than 1, and beta is less than 1/2. And, this is so to speak about the intensities, and then of two birds, one can see the other, or both can see the third one. Das heißt, für any two birds, I and J, I is in this set, seen from J, or J is seen from I, or there is a third one, which both can see. This is this principle of the third agent, or the scrambling property.
You never mentioned anything about the locations of the birds.
Yeah.
Just the velocity.
Yeah.
They also stay together in this group? Are they break into groups or?
I will not talk about this. I will only consider the velocities. If you put on that one more condition, the strengthening, then you will find that the positions stabilize, which of course is an important feature of a swarm. Yeah, let me skip. Here's a sketch of the proof. I will skip it for now. If someone is interested in, I could explain this. But one thing I should show here, the role of this beta in the model of Cucker-Smale. This case beta less than 1/2. This means that this integral is infinite, and this means the intensity of interaction is strong enough. So this is the role of beta connected to intensity in this way. Okay, it's already interesting here to look at particular cases. The Cucker-Smale flocking means every bird can see every other. Right? But now, being unsymmetric, one can allow some leadership. This means there is a bird seen by all the others. Or non-leadership, maybe the view, a different kind of view, and there is a trade-off between intensity and structure, making the beta in this model smaller. The requirement on a bird's view can be weakened. So there is a intensity and structure. If one thing is lower, the other for a swarm must be greater, and vice versa. And there's also, this is a line formation which you also can see. There are the birds, and each sees another one, which is before. Okay. And this is a kind of hierarchical leadership. Okay. Now the interest is what biologists observe is there is sometimes a leadership in also the fowl formations, but this leadership changes with time. From time to time there will be a different bird leading in this fowl formation, right? And this means that when looking at the set S of I, the bird seen by bird I may be different from time to time, which is not the case here. So next question is, what if formations change in time? Which is the case, as biologists say. And therefore, find the tool from opinion dynamics I had before. So, situation is this: we have an agent, 10 birds, something else, sitting in d-dimensional space, depending on time, and there are interaction coefficients, and the movement, the dynamics is given by this difference equation. So, because the coefficients are like this is the kind of averaging, time-dependent averaging. And consensus, if you think of opinion dynamics, will be reached, meaning this, for all I, holds if they exist. Let's come some assumptions. This is a model, this is a result I want to prove, consensus, equalization of, asymptotic equalization of the velocities. I need some assumptions for it. So this will be more general now because I want to model and picture the change of formations. Okay, assumptions. There is a function, the intensity function, and now there is a mapping which allows to describe the switching between formations. So some make this for k is fixed. Sequence of time periods, one after the other, but the distance should not be larger than some r, such that the following is true. We have here again, the interaction is bounded from below in intensity and by some structure. The structure was fixed before, but now it may change with time, with this period here. And those are, of course, non-negative matrices. And maybe the most interesting point here is I require the assumption which will follow not for each point in time, but only for certain points in time. In between, the birds may do something different. And this is why it is not a mathematical structure, you see. There's something in between, but from time to time, certain assumptions are met. And they will follow. Again, intensity of interaction decay is not too fast. This is an assumption here on this function. This is for all time points. But the structure of interaction becomes not too loose. And this means the following. You have various regimes of interaction given by these matrices here. And the composite of those matrices in this way is scrambling for every n, and also this coefficient is bounded from below, the intensity is bounded from below by this function. So you have again the scrambling property, or you might say principle of the third agent. This is, I mean, birds, one can see the other and the other way around, but the important thing is needed here is if you have two, there should be a third one, which both birds can observe, and trying to average the velocities with this bird.
Sorry, I don't understand the meaning of the composite of regimes. It means that for each matrix has this property. At any given time in which there is change in the formation,
Yeah.
then there is a third, every two birds that's
Yeah.
just a third one.
This-
Every time.
Yeah, for the whole product, this is required only. Not at each moment.
Okay, it can be that at some moment in which there is change in formation, two birds don't see each other.
Yeah.
But at some later time, there should be a third.
Right.
Okay.
Right. Maybe the following will explain this a little bit better. So, various regimes of flying. So, S of I and T is a set of birds seen by bird I at time T. This set may now change. Changes with the bird, different for the birds and also in time. And so this gives different regimes of sight. Here is some bird at those particular moments in time, Tm. Possibly at random. The birds may, between the points T1, T2, T3, and so on, behave randomly. So here is the time axis, discrete time, 0, 1, 2, 3, 4, etc. And here are the particular moments in time. I'm making some assumptions. T1, T2, T3, T4, maybe the distances may be small or large, but the maximum distance should be finite. And here you have the regime A sigma 1. So regime of interaction is described by a matrix. So this is a certain matrix related to this point of time. And here's another regime described by a matrix for this point in time. Again and again. And those correspond to a certain view. The set of birds seen by this bird point at time t1. And this, they may see in time different birds. So arbitrary behavior, this is an important point. In between, there might be no sight. For example of this is changing leadership. So at one Tm, point in time Tm, each bird might see a certain bird Km. But, so this is a leader. But at another time point, this may be a different bird. So this models changing leadership. There's a bird in front, but next time point in the and this means then, in this case, for this particular matrix, the column Kn is strictly positive. And this means, in particular, then, that the matrix is scrambling. It need not be a single matrix with scrambling. It's a product, but in this particular case, you have that the single matrix is already scrambling. Now, this was starting from the Cucker-Smale model, introducing some concepts from opinion dynamics, having in mind that trying to get the same velocity is something of a consensus finding among birds. And I use tools from opinion dynamics that to give assumptions for having for the swarm is forming. Now I generalize it further. And again, we have n birds, 1 to n time points, discrete time points. This is the velocity, and this is the average definition of velocity. This is the averaging principle. And this is a set of birds seen by bird I, J. So this is the meaning interaction. The communication is about interaction. This is the main principle biologists say, but there are others. Maybe also some acoustic signals, or generally speaking of signals is possible. And then we say a subset of birds, non-empty subset of birds, is saturated at T whenever this the case is. If a bird is in the set, then all birds seen by I are in the set. So saturated in relation to C. Now I suppose that at each point in time, the regime is coherent, which means any two sets saturated in the sense at T have a non-empty intersection. Now here's the theorem. The result I want to obtain is flocking or swarming. That means velocities are asymptotically approaching the same value. Then I assume there's a time sequence as before, and the distance, the maximal distance between any points in time I consider here is finite. Furthermore, at every of these particular points, the coherent the flight regime is coherent. For every, as I said, in between they might do anything. Now, for simplicity, I define the set seeing so that I is contained. It sees, the bird sees himself. You might not do that and treat it separately, but this makes things a little bit more complicated to model. And it's no additional assumption. Now, this maybe is a thing most difficult to understand. I define here the minimal interaction, alpha of t, at a certain point in time. And this is the minimum following. This describes the interaction between bird I and J at some of the particular points in time, but I take the minimum over all the special points in time before some t I consider here. Right? And this is the same. Here is for different birds, I different from J, but here I consider what's also called self-interaction. And the assumption is that the minimal interaction defined in this way decays not too fast, meaning this integral over the intensity, the powers come here in and play a role, is infinite. So in principle, the meaning as before, this is with respect to the assumption with respect to the intensity of interaction, and this is an assumption with respect to the structure. The structure should be coherent in the way I defined it before. Okay, I will again skip the proof. Let me just mention, there's some theorem. I mean, there are several, but one is interesting. There is a type of matrix called the Rimsov matrices. Those are not so, non-negative matrices, they are not so well known. They were invented by a Russian mathematician around 1920s. Old stuff, very useful here. And there's a theorem by Hartfield, American mathematician. You can do something here. I have here the definition, but I will skip that. But here comes something from the theory of non-negative matrices in. Okay, a flight regime at T is given by the sets here. Who sees whom? Which may change in time. And the core at T is the intersection of all sets saturated at T. In a minute I will produce a picture, and this will explain this or make this more visible, I think. Then what plays a role is a side chain from I to J. That means, I mean, if you have two birds, you can talk about this bird sees this one. And the side chain is, if you have here a bird sees this bird sees this bird, this bird sees this bird, this bird sees this bird. Right? This is the definition here. And the proposition here is, for any point in time, and the sets include the I, a flight is coherent if and only if a side chain of each bird into the core. So there is some structure, there is a core, in a minute I will make a picture, there is a core of the flying birds, and there are side chains. Other birds who can see indirectly via other birds, someone from the core. Okay, here are some examples. The core is a single bird, star. Leadership means, okay, here is a board. I will draw some pictures here of the various forms of formation. First one is leadership. So it means here a star, certain bird, and okay, this is simple. All others. Right. This means viewing, seeing. This is leadership interaction. And there is one seen by all the others. And more interesting, I think, oh, no, this is not more, this is line. So there is one bird here, 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 here. So the indirect way of seeing. And V formation, this is star is here, and you have two lines, two line formations, so to speak. This could be shorter or longer. An echelon. This is interesting. Can you see that? Something like this. Okay, let me draw it this way. Can you make any sense of it? I mean, instead of drawing single points, I made these lines, and on this line are sitting birds. This is a V kind, but in many ways. This is an echelon. Okay, star at the top. Okay, and then says the birds may have one of those formations at certain points in time, and from certain special points in time they may change from this to this to this, or if you have this one, the leader could be changed. The same form, but different leader. Or it could be a different form. Or it could be this form. Actually, this form one can see very often of smaller birds, but also made by geese. There's a spectacle at the sky, and you see this, and long, big swarms. And this is where the core, this is the core here. The core are those birds which are seen directly or indirectly by all the others. So this is seen directly by this one, but indirectly by this one. And here we have this one is birds directly or via some path indirectly. Now the more difficult case is if the core is a cycle of several birds. There is not just one bird in the core. This means there are lots of birds seen directly or indirectly by all the others. For example, could be, what should I do? 3 birds which can see each other. This bird can see this one, this means the arrow here. This can see this one, this can see this one. Of course, indirectly this bird sees this one via this bird. Right? Now, there can be, let's see, whether I the same principle, but different orientation of seeing. And of course, this bird cannot see this one. But if this bird can see this one, then he can see all those. This one can see all those. but not this one. But if I put the structure this way, then each bird can see the other one. Right? Directly or indirectly. Now, this is core, and then there might be others. For example, might be a line here to this one, or it might be, okay, this, or here, a fuller echelon. We might have such a formation. And this looks different. I mean, this you can see in autumn also really a fantastic way made by the birds. But what about this one? Have you ever seen a swarm like this? No. Well, I mean, could you imagine where? I mean,
but if we would use rotations at the very end too, the wave will not follow. I mean, we will stay basically on the same place and just going around.
Going around, it could be if they are landing, for example. Some are going this way, others turning around this way, and the others coming there.
Okay.
Could be. Or, and I'm not sure about this, this is still a point of research, considering this more complicated case too, was of course a cycle, whether this is of some help describing swarms of starlings. For example, of a Rost in Rome, it's famous, big swarms of starlings, and going like and many thousands of starlings, and there seems something inside, some hidden leadership, difficult to see. So this would be a next step to think about. And okay, this we had echelon composed of different cycles. Here, for example. And also, one has to discuss it. If one wants to discuss the formations, in some sense optically, one has to think of 3 dimensions. Whirling around. It's very difficult. There's a group in Rome, the members of which observe doing some experimental work. And I mean, this is not, these drawings are not really wonderful. Rather poor, of course. If there's someone in the room who is interested in the stuff and is able to make computer simulations, it would be very nice to do some computer simulations on the basis of the classification of forms we have, and now observing maybe the change from one formation to the other and so on. And then the big thing would be to make it of those starlings over Rome, some computer simulation led by the concepts and so on forth represented. And now the final thing. Oh yes, this is something, some conclusion. I mentioned this already. The swarm will be coherent at certain points in time, but free in between these points. And examples I talked already in some sense. Free movement, then, for example, line formation, then there may be in between the time points, the special time points, free movement, some restructuring, maybe by random, line formation again, led by another bird, or another formation again. Now, this is just saying you can have those formations and change in time. Composition of different regimes. And I mentioned already some references. This is Chazelle, the paper I mentioned, the long one, very interesting paper. Then Cucker-Smale already two, these are already on that issue. Then simplification, simple proof by Ha and Liu. And the hard field I mentioned, this is a book on non-homogeneous matrix products. Important thing in positive dynamic systems. And then the model I did with Rainer Hexelmann, bounded confidence. But I was not talking about this today. But let me mention, maybe some of you know this famous model of Robert Axelrod about the dissemination of culture. There are similarities to this model. But this model is, like the model of Cucker-Smale, this model is symmetric. And the Axelrod model also is symmetric. And for symmetric models, you can say mathematically you can prove a lot. The swarm models, as I described it, are asymmetric. And you need different tools to handle those. Okay, this. Then something in swarms. Then this is a book mentioned already by Raoul. This is a very interesting article by biologists. Organized flights in birds, in animal behavior. I learned a lot from that paper. For example, I never heard the word echelon before. This is another interesting paper about experiments made with swarms. And this is probably some of you know this paper by Reynolds, rather old one. Flocks, herds, in schools, a distributed behavioral model, computer graphics. And there's no proof in that paper. But he described in a nice way 3 rules observed by birds. I was only talking about one rule, aggregating, averaging the velocities. There are others, as Raoul mentioned before, talking about the position. One needs another rule. Also, he did this pioneering paper, and then he made a computer simulation. He didn't prove anything. He made a computer simulation. You can see it on the internet. And if you look at his simulations, you think there are swarms of birds on the screen. This is fantastic. Thank you very much for your attention.
Thank you for this talk. Any questions?
I don't know which part of your assumptions imply that there is a leader. I mean, in some parts of your talk it's clear that you should have a leader. In some others, you should have a leader which is changing in time.
Yeah.
But can you, for example, for the Starling example that we see here in Mallorca a lot, the people say that there is no real leader, that all of them are equal.
Yeah.
But so I don't know which part, so you have some assumptions that imply that you may have one leader that later may change.
Yeah.
But does anything, any of your results apply to a flock without any leader? Is this?
Yeah. I mean, the hard point is to do it without leaders. And so I make no assumption on any kind of leadership. Those are just cases, I admit. There are some cases in biologists report on those cases. So just to mention the cases, but there's no assumption of leadership. And actually the interesting case is there's no leadership at all. That's right, yeah.
I have a question concerning your assumption that the coherence is only defined at certain discrete points in time. And how far does that affect, because I think it's introduced in order to allow transitions between the different configurations.
Yeah.
And how far does this influence or affect actually the possible transition? Because one could equally assume to have a certain amount of incoherence at any time. So what is the consequence of this assumption that in discrete moments of time you have coherence and between not necessarily?
Yeah. Also, it is this way. At certain points in time, there should be some contractive behavior in some sense, some averaging behavior. Those assumptions. But then they may do anything. But then there should be a point in time where again it is contractive. Right? So it is allowed to move freely, but there should always be after that a point in time where there is some averaging.
By that you impose the transitions in the configurations because you let the system be free in between.
Yes, they can free in between. It is something like there's a new starting. I mean, they start here arbitrarily. Then there is some averaging. The rules are satisfied. They move free. Means there is a new starting point. And there could be different starting points in time.
Okay.
Yeah, but your results apply to the limit when t goes to infinity, I understood.
Yeah.
So how does it coincide with this existence of preferred times in which there's coherence?
It should always be a next point after free movement should a point of averaging. Because there are infinitely many points of averaging required.
But there's less than r. R was the time which these times were separated.
Yeah.
R had an upper bound.
Yeah. Yeah. So
I don't understand this behavior with the limit when t goes to infinity.
Yeah.
With asymptotic behavior.
Yeah.
How can you have an asymptotic behavior if it goes switching from one place to another?
I'm not sure that I understand. I mean, it is what's not possible to form a swarm is, and there are examples, that they are averaging here at this time, then moving freely. Next point, averaging. Then moving freely. Next point, averaging. And then the distance becomes longer and longer between averaging. So moving freely becomes more and more dominant. That's not allowed. Therefore, it is assumed that the maximal distance between two averaging moments is a finite one.
And then is there an asymptotic regime they reach in which the velocity is the same for all of them? You reach an asymptotic...
They are approaching this. So, about consensus is only for t going to infinity. So, in between, they may not have reached a joint velocity. But if there will be a process of averaging again and again, then asymptotically they will tend to reach a common velocity. That's the story.
I think that the point is that you are not, when you say there is a point of averaging in free motion, I think this, tell me if I understood correctly or not. Your dynamical system is always positive. It's averaging. All the time is averaging. It's only at particular times that the averaging is strong enough to satisfy some bounds. Is this the case? But is this or not?
Yeah, right. Yeah, sorry. I did not. It is always averaging,
Yeah, it's always
but it may be weekly, not without any rule. Yes, that's I should have said this. It's always averaging, but the assumptions, stronger averaging, apply
Some moments is
only.
particularly strong.
Yeah. Yeah, that's important, because otherwise they could fly by something away. So the model is for each point in time, but the assumption is only for some special.
I'd like to come back to the question of leadership.
Yeah.
The very interesting question is the emergence of leadership. It is not that there is a bird which is special because it has something special and he is the leader. What you try to do is you describe structures in which someone plays the role of a leader.
Right.
But the question is how dynamically this thing emerges from individuals which are all equal. It is the emergence of leadership, because otherwise it comes to these ideas of biology, no, this is a special bird. There is no special bird. It's an emergent property.
Yeah.
And that's what would be, from my point of view, interesting to describe how it emerges.
I agree with it, but I don't know nothing about it. And I have not tackled this problem, this is important, how leadership may arise. Maybe necessary also.
Well, it is in the dynamical rules.
Yeah.
In your dynamical rules, there is no anything special about any of the individuals.
Yeah, right.
Except the
Matrix
site.
is
Except the site.
That's
it has a matrix that has some hierarchy on it. You can put that.
But that's a description of a situation after some time. The question is how do you reach there? Starting
Well, the
from.
matrix is static.
No, it depends on time.
This is the point in swarms, as you mentioned. The interesting thing is there is no leadership. Consensus, or there is a formation without any kind of leadership.
Well, my point is that perhaps leadership means two different things. There is no leadership in the sense that there is no one causing the flow to be formed.
Yeah.
But the dynamical rules lead to the emergence of a leadership role, which is a difference.
Yeah, I understand. Yes, that's a very interesting point. Here you find if the core consists of several birds, this is a kind of leadership with respect to the others. But I only describe it. I don't explain why and how this happens.
Okay. Any other questions? No, we thank Ulrich again for the talk.